Frequency, when they use the word frequency, they're talking about what happens in a certain period of time. You know, everybody's familiar with what a sound wave looks like. And a frequency is how many times that sound wave happens. For ultrasound, it's every second. So whenever we talk frequencies, the time period we're talking about is for a second. Now they group sound into 3 different categories. Infrasound is sound that'll have less than 20 cycles like this every second. That's sound that we cannot hear. Then there's audible sound. That's 20 cycles, or the common term they use is hertz. How many cycles per second is how many hertz per second. 20 to 20,000 is what we can hear. That's high-pitched voices of little kids to elephants, you know, talking over great distances in stuff that we can't hear with our ears, but naturally they can and still considered audible. And then there's ultrasound. And ultrasound is sound waves that have 20,000 to 17 million cycles per second. We have some transducers that tell, you know, they're 17 megahertz. That means they put out 17 million cycles per second. The more you know about ultrasound, the more you know about how much information is happening all the time, and how noise in an ultrasound system, stuff not working right, can affect its ability to provide the product that you want. A frame rate is how many sets of images you see per second on an ultrasound machine. An ultrasound machine, when it's sending out its pulse wave, you know, if this is time right here, and this is going to be 1,000th of a second, it'll send out 3 little pulses, and then it'll listen, and then it'll send out 3 more. It pulses. It'll do that 100,000 times a second. Send out the sound, then listen. On your transducers, crystals on your transducers, the electricity coming through the wire excites that crystal, sends out that frequency, and then that same crystal, when it stops vibrating and sending out sound, it becomes, you know, like a stethoscope. And that sound coming back, it comes back in, sends the information back to the computer in the ultrasound machine, and that's where it starts doing that. So it shoots it out and listens. And the amount of information it shoots out, on average, it gets about 2% of that information back. Otherwise, remember, that sound has to go out. If I've got a little ball right here, it only comes back to me if I hit it on a flat surface. If I bounced it off the top of that podium, it would hit that, and it would go off that way and never come back. That's how sound is. It's got to come right back to me. So about only 2% of the signal comes back. So that's why it's important, you know, for that machine to be putting out the appropriate amount of power that it's set to do, so that it can get as much information back. So the frame rates are, it may do 500 of these pulse listen, takes out all that information. The information that showed up more times than it didn't, it makes that one frame. It takes 24 of those frames, and that's your frame rate. For the most part, all transducers that provide an image today are pulse wave. You know, they'll have 96 little elements in the end, and those elements, like I said, will excite, send out noise, stop, and listen back. A continuous wave transducer, anybody besides Steve? How many crystals in a continuous wave transducer? Be right ahead. 2. Exactly. Continuous wave transducer has 2 crystals. One crystal is always sending out information. The other one just listens. The benefit of that is purely for Doppler imaging to look at stenosis, high velocity areas. With the pulse wave, if you get high velocities, we'll talk about Doppler next, the velocity will come back so quick that it'll run into your sound wave and you get aliasing. And so that kind of segues in where continuous wave, you're sending it out, this one over here is listening, and it'll track the velocities. It'll track the velocities to a T. Doppler technology comes from the 1400s when astronomers and astrologists used to use the difference in the light waves coming from stars to track which stars were moving away faster than others. How they did it, I have no idea. But the Doppler shift, as it was known by Dr. Doppler, was that an object or material, sound is energy, moving closer to you will represent a higher frequency or a higher color band than sound or energy moving away. So you know that old adage of the race car? You know, if you're watching NASCAR on TV and it's, well, it didn't shift gears right in front of you. The car has the same sound the whole way. It's just that sound being emitted while the car is coming towards you increases the frequency or how many of those sound waves hit you. It appears to be a higher pitch. As it's moving away, same noise it was making as it's coming towards you, but those sound waves are lengthened out because there's fewer of them hitting you because it's stretched out from the car. So that's the same principle that applies to ultrasound in the 2D and ultrasound in the Doppler imaging. Just to finish it up, so continuous wave transducers for the most part today are just used in the brain. That's where you can get stenosis of the fine arteries, very high velocities. Velocities get too high, that's too much back pressure, and the artery could blow out before the stenotic area. That's when you have a stroke. So continuous wave is pretty much just used for transcranial stuff for the most part anymore. So you probably don't move a whole lot of those. 20 years ago, when the 2D technology wasn't there, they'd use continuous wave on hearts, you know, and stuff like that for the arteries on the hearts. But now 2D kind of covers that, so they don't need to. So I wouldn't think you move many of those anymore. Whereas 20 years ago, you couldn't sell a cardiac machine without. Everybody wanted one. Aliasing is a confusion of information when it's regard to color Doppler. You're sending out the information to see which direction it's coming. It's coming at you so fast that you're still doing your pulses when it bounces back, and you don't get your red or your blue. You get, you know, the tumbling and the aliasing. You know, there's another Dr. Nyquist came up with an equation for that. If you're trying to minimize the amount of aliasing, you use the highest color frequency that you can, and that will help you reduce the amount of aliasing that you do. So aliasing is just sending information running into receiving information, is what happens with aliasing. So what's it been? Compound imaging's been popular now for maybe 8 or 10 years. Compound imaging is the method of striking the same point with a transducer. Let's say we've got a little ugly right here. And this is in a lobe of the liver. So we've got the ultrasound beams, you know, they come out of the transducer. And they hit the structure. That's kind of a standard ultrasound beam right there. Compounding can happen two ways. The most common way is the transducer then, each one of these crystals will not only shoot up straight, but it'll shoot at an angle. So by compounding, we'll hit this way, start hitting it this way. You hit the same object from more angles, and you get better border detection down low. It doesn't really do anything for you up top, but you'll get better borders on the sides with compounding. Ultrasound is a business of trade-offs. If you want to get more information in an image, you're going to get less frame rates in an image. It's a trade-off. If you have a machine that is more sensitive to color, it's going to be less sensitive to grayscale. When you do compounding, when you do more with an image, your frame rates will reduce. This isn't quite squared up for some reason, but our frame rates are right up over here in the corner. And so you can see when I try to do more with an ultrasound image, meaning if I'm going to be shallow, I can run at 52 megahertz. If I really want to scan deep, it's going to take longer to get the sound down there and back. My frame rates are going to go down. If I want to use color, again, I'm going to task the machine, and it's going to even give me slower frame rates because I'm doing more information. So with ultrasound, you only want to do as much technology as you need to maintain the higher frame rates. As well, it's one of the questions in here, you want to operate at the highest frequencies that you can at all times.